Today we're going to talk about slope fields. This is day 2 of differential equations, and I'm just going to pull up the worksheet that we've already given you and kind of use this as a guide. So first of all, let's define a slope field. Given a differential equation, which let's recall that's just an equation involving a derivative, given a differential equation dy dx is equal to f of xy, the slope field for the differential equation is obtained as follows. At every point xy in the plane, we place a small line segment. The slope of the line segment at the point x comma y is determined by the value of dy dx at that point. So I've given you 3 examples here, and let's just take a look at each of them and try to understand how this picture comes from this differential equation. So let's look at the first slope field here. What I want you to do is take a look at the line segment at the point 0, 2. So let's look at the line segment at 0, 2. So that would be this point right here. So 0, 2 would be this point right here. Now you should notice that the slope of this line segment is 0 because it's flat, it's horizontal. The reason that this particular line segment is flat, the reason that this particular line segment has slope 0 is because when you plug the point 0, 2 into this differential equation, you get 0, right? If you plug 0, 2 into the differential equation dy over dx is equal to x over y, replacing x with 0 and y with 2, you get 0 over 2 is equal to 0. So in other words, recapping, the reason that this line segment at the point 0, 2 has 0 slope is because when you plug that point into this equation, you get 0. And that's what dictates the slopes of all of these line segments. The slope of each of these line segments is obtained by taking the coordinates of the point at which the segment sits and plugging them into the differential equation and seeing what you get. So let's take a look at another example. So staying with the same picture, let's look at the line segment at the point 1, 2. So 1, 2, where would that be? 1 over 2 up. Oh no, we want to look at the second slope field, excuse me. So let's look at the second slope field, and let's look at the point 1, 2. So if I go 1 over and 2 up, that's this point right here. Now the slope of that line segment at 1, 2, it's negative 1. Why is it negative 1? Because if you plug this point 1, 2 into this differential equation, in other words, replacing x with 1 and replacing y with 2, you're going to get 1 minus 2 equals negative 1. So what determines the slope of this line segment? Well, to find the slope of this line segment, you just take the coordinates of the point at which this line segment is sitting, plug them into this differential equation, and find and evaluate. And that's the slope of the line segment at that point. So the slope of every single point in here is determined by this differential equation, right? And over here, the slope of all these line segments is determined by plugging the coordinates into this differential equation, and so on. And that's how a slope field is generated. Now, generating a slope field by hand, these were generated by computer, generated by slope field by hand is pretty tedious because you'd have to plug every single one of these points into this differential equation, write down the number that you get, and then draw a little tiny line segment with the slope that you just obtained. We'll do a little bit of that. We won't have you plug in too many points, but for the most part, this is something that we have computers do. So we'll have an opportunity in a minute to actually sketch our own slope fields from a differential equation. But before we even do that, I want to talk about why we are talking about these things. What is the meaning and importance of these slope fields? What is the meaning of these things? So let's have a look. Every differential equation has an infinite number of solutions. Remember that yesterday? If you have an initial condition, then that initial condition narrows the infinite number of solutions down to one and only one unique solution. Remember, the initial condition determines the value of c, but without an initial condition, a differential equation by itself, without an initial condition, has an infinite number of solutions, okay? And each solution, remember, is a function. And every function has a graph. So if you have a differential equation, and you look at all the solutions, that's an infinite family of functions, and you graph all those infinitely many functions on the same plane, then you get a picture like this. Okay, in this picture, what I've done is I've graphed many, many different functions. It's all the solutions, or many of the solutions, to a certain differential equation. Okay, so this shows the graph of the solutions. This picture here shows the graph of the solutions to the differential equation dy dx is equal to x over y. If you solve this differential equation, this one here, using separation of variables, you obtain the general solution, this thing right here, okay? And this picture is obtained by graphing this function for different values of c. If you let c be 0 and you take the plus and the plus minus, then I believe that you get this straight diagonal line right here. If you let c be 0 and take the minus, then you're going to get this straight diagonal line right here. If you let c be 1, then I think, and you take the positive sign, then I believe that you get this curve right here. Okay, and taking different values of c just gives you different curves. So this picture is a graph of every single solution, or at least many solutions, to this differential equation in the same plane. Now, what I want to do is go back to the first slope field in the previous section and take a look at the similarity between this picture and the very first slope field we looked at. So let's go back. Compare this picture here with this picture here. Do you see the similarities? This differential equation here is the same as the differential equation here. So what's really happening? Well, what's happening is the slope field associated with the differential equation is kind of like a rough sketch of this thing right here. It's a rough sketch of all of the possible solutions to the differential equation for different values of c. Now, you might wonder, why would you care about that? Why would you go through the trouble of tediously plotting all these little line segments and giving yourself kind of an approximate picture of the solutions? Why would you do that when you could just literally solve the differential equation and then actually graph those functions, not approximately, but perfectly? Why would you settle for an approximation? The answer is that many differential equations cannot be solved. Many of them cannot be solved. The method that we have, separation of variables, in truth, it almost never works. It works on a really important class of problems, but there are many differential equations for which separation of variables doesn't work. And in fact, there are a great many differential equations for which there is no way of finding explicit formulas for y. And when that's the case, it's great to be able to construct the slope field, because even if we can't get the solutions, we can get a pretty good picture of the solutions by constructing the slope field. The slope field, is something that pretty much, someone in middle school could do, right? It's just plugging points into this equation. No calculus required. So even if we can't solve the differential equation, we can still construct the slope field. And that slope field, as we see, comparing this picture to this picture, is a pretty good approximation of what the infinite family of solutions to the differential equations looks like. So that's why we care about this. Now, if you remember from yesterday, we had this notion called initial conditions. Sometimes a differential equation would come along with an additional piece of information called an initial condition. And what the initial condition would do is it would narrow down the infinitely many solutions to a single unique solution, right? Differential equations in general have many solutions, but if there's an initial condition, then there's only one solution. So how does that look when it comes to slope fields? Well, it's the following. Here I have, once again, sort of a picture really pretty much the same picture as here, except I'm using dashed lines instead of solid lines. And let's suppose that in addition to having this differential equation here, suppose that we also have the initial condition y of 0 equals 2. Now, what this initial condition is saying is that when x is 0, y is 2. Interpreting that geometrically, what it's really telling you is that the graph of your function goes through the point 0, 2, right? If I tell you that when x is 0, the value of the function is 2, that's telling you that the graph of the function goes through this point. And you can see that there is in fact only one curve which goes through 0, 2, which I've highlighted here with the solid line. So yes, there are many, many solutions to this differential equation here, right? All of them having this form, a different solution for each choice of C. So there are many, many solutions to this differential equation, and hence many curves in this picture. But once I put in an initial condition, that initial condition says I'm actually looking just for the solution which goes through this point, 0, 2, and there's in fact only one such curve, okay? It's not an accident that there's only one curve going through that point. That will always happen, okay? So if you have a slope field of a differential equation and you want to sketch a particular solution corresponding to some initial condition, here's what you can do. You locate the point in the plane corresponding to the initial condition, and then you follow the slope field with your pencil. You pretend that the slope field is like an ocean, and the line segments tell you the direction of the current. You're in a little boat, and your boat begins to travel, begins at the initial point. And what you do is you trace the path that your boat follows, okay? So this path here is kind of obtained by imagining that each of these little line segments is a direction of current. If I go back to my original picture here, if I imagine starting right here, you can see that the current is telling me to go this way, and then it's telling me to go this way, and then it's pushing me this way, and you can kind of see that U-shaped curve emerging if you imagine that these are lines of current. We'll do an example like that in a moment. Okay, so let's actually get to some of the problems. Sketching slope fields and matching slope fields with differential equations. One way to sketch a slope field is to plug every single point into the differential equation, then draw a line segment with the appropriate slope. This is extremely tedious. The AP exam often gives students a single differential equation, presents 4 or 5 slope fields, then asks the student to select the correct slope field corresponding to the differential equation. So you don't have time to reconstruct the entire slope field for yourself. So what's a better method? So in general, there are a couple of things. I think these instructions actually are maybe better placed down here. Let's postpone matching differential equations with their slope fields for a moment, and let's just actually take a moment to, even though it's tedious, construct the slope fields for some of these differential equations. So what I'm going to do is I'm going to go through number 1 with you, and we're going to sketch some of these solutions. I have these pictures in a graphics program here in my browser, and we're just going to try and sketch the slope fields for each of these guys. So let's focus on this first differential equation. It's given by dy dx equals 1 minus y. And what I need to do is draw a little line segment at each of these points that have been indicated here. So the way that I'm going to do that is I'm going to start, let's say at the origin, doesn't really matter where I start. The coordinates of this point are 0, 0, which means to find the slope of the line segment that I'm putting with 0 and y with 0 in my differential equation. Now x doesn't even appear in this differential equation, so I'm just replacing y with 0. I replace y with 0, I get 1 minus 0, which is 1. Therefore, the slope of the line segment that I draw here is going to be 1. Oops. So something like this, okay? Line segment 1. Now if I go over here, this point is 1, 0, all right? Now, if you think about it, plugging 1, 0 in, 1 for x and 0 for y, you're going to get the same answer here because actually this differential equation doesn't even depend upon x. So the fact that the x-coordinate has changed from here to here doesn't actually make any difference. If I plug 1, 0 into this differential equation, I still get 1. And if you think about it, all of these points here have to have the same slope. They're all going to have slope 1. The differential equation doesn't depend upon x at all. So changing the x-coordinate will have no effect on the slope of the corresponding line segment. So I kind of can save myself some time there. Let's maybe go up here. The coordinates at this point are 0, 1. That means that the y-coordinate is 1. If I replace x with 0 and y with 1 in this equation, I actually get 0, right? Because the y-coordinate's 1, 1 minus 1 is 0. So I'm going to get a flat line segment here. And by the same argument that I made a moment ago, each of these is going to be slope 0 because, again, this differential equation doesn't even depend upon the x-coordinate. So I know that all of these guys have to have the same slope. This guy here has coordinates 0, 2. Plugging 2 in for y here gives me 1 minus 2 is -1. So this guy is going to have slope -1. And again, using that same argument, they're all going to have slope -1. And we can proceed further, and you can figure out the rest. Let's maybe have a look at this differential equation. Here, I'll just do a couple of them. No, I just want to move. How do I... Bear with me here, folks. Just trying to scroll down. I guess I can do it from here. So let's have a look here. Now we're working with the differential equation x plus y. The origin is 0, 0. If you plug in 0 for x and 0 for y, you get 0. So that's going to be a horizontal line. Maybe I'll pick this point right here. This point is 1, 1. Replace x with 1 and y with 1, you get 2. So I'm going to draw a line of slope 2. If I take a look at maybe, for example, this point right here, this is 0, 1. So I'm replacing x with 0 and y with 1. That's going to be a line of slope 1. This point right here, it's -1, 1. If I replace x with -1 and y with 1, you get -1 plus 1, which is 0. So I'll draw a line segment of slope 0. And you can see how the rest of it goes, right? I don't think we need to see any more of that. Pretty clear how this works. One quick thing, this differential equation here, certain points will give you undefined values. For example, if I plug in 0, 0 into this equation here, you get 0 over 0, which is really, if you remember, 0 over 0 is a indeterminate quantity, and you should really probably not even plot anything, I think. On the other hand, I think that if you pick this point here, 1, 0, or rather this point right here, let's have a look at this point. It's 0, 1, right? If you replace y with 1 and x with 0, you get -1 over 0, which is essentially some kind of infinity. That's telling you that your slope should basically be vertical, okay? So, you know, just like if you were taking a limit and you get something like 3 over 0 or 2 over 0 or -5 over 0, you know that's some kind of infinity. So if you have a line segment with infinite slope, that means it's basically vertical. However, the exception would be the origin here, because plugging in 0, 0 gives you 0 over 0, which is really an indeterminate quantity. I would be very hesitant to say, you know, what exactly is happening here. I probably just wouldn't draw anything. Okay, so let's go ahead and move on to the second set of problems, which has us matching different differential equations with their slope fields. These are the kinds of questions that the AP will ask you. They love this kind of question. They always appear on the tests. And, you know, how do you do this, right? Because we've got all these different differential equations, all these different slope fields. What you don't want to do is tediously plot like every point, you know, for each differential equation, try and match up. So what I want to point out is that there are certain tricks, okay? Let's take a look at A. Let's think about this differential equation. What slope field could satisfy this differential equation? I want you to notice this differential equation doesn't depend upon y. The right-hand side does not involve y at all, which means that the slope of the lines should not depend upon the y-coordinate, Okay, so in other words, changing the y-coordinate in the correct slope field, the slope field belonging to this differential equation, changing the y-coordinate shouldn't affect the slope. So which slope fields have that property? If I change the y-coordinate here, does that change the slope? Yeah, it does seem to change, right? Do we see that here? It's very steeply positive, and then here it's less positive. Changing the y-coordinate changes the slope in this slope field, which means this slope field can't belong to this differential equation. So I can rule that out right away. This one here, again, the slope changes as you vary the y-coordinate. So this can't be the one that matches this differential equation. Same thing here, we can rule it out. Same thing here, we can rule it out. Same thing here, we can rule it out. This one, though, looks promising. If we have a look at this slope field, number 6, as you change the y-coordinate, as you move up and down, the slope doesn't seem to change. It's flat all the way through here. Here it's like -1 maybe, just all the way through. As a matter of fact, this is the only slope field which belongs to, which has the right property, which has that property where the slope doesn't change as you vary the y-coordinate. So this one has to be associated with A. Okay, so that's one key trick that you can use in matching up slope fields in differential equations. If the differential equation only involves just x or just y, then you know that there's going to be some symmetry, and you can look for that symmetry to figure the right answer out correctly. This one here only involves y, doesn't involve x at all. That's telling you that the slope field corresponding to this guy has to be invariant as you change the x-coordinate. So whatever slope field belongs to this one, it has to have the property that as you change the x-coordinate, the slopes of the segments don't change. Of course, that also has to be true for this one. So thinking about that property in and of itself won't be enough to tell the difference between these two. I would expect there to be two slope fields which have the property that, the slopes don't change as you move left and right. Let's just quickly try and find them. This looks like a good candidate, right? As I move left and right, as I change x, those slopes don't seem to change. So this guy could belong to 1. Looks like it could also belong to 2, right? Again, as you change the x-coordinate, the slopes don't seem to change. And so this slope field doesn't depend upon x. So I think that B and C probably belong to 1 and 2. But we'd have to think a little more carefully about which one it is. Actually, we can sort of do that right now, and it'll bring up another trick. Notice that C, this differential equation here, because it's got a y in the denominator, it's going to be undefined for any time the y value is 0. Okay. I know I said a moment ago that it might make sense to, to draw vertical lines, but I think that, in a rendering program like this, vertical lines won't be drawn. You can see that when y is 0 in this picture, there are no segments drawn, and that's corresponding, I think, to the fact that the slope is actually undefined, right? This differential equation is undefined at these points. On the other hand, if you look over here, the slopes are 0 when y is equal to 0. So this one can't belong to this differential equation, right? I think that belongs to B. So 1 and B, and then C and 2 go together. Another, sort of, let's sort of think about how we might distinguish between E and F. Like, what else can you look for? One thing that you can look for as well is thinking about the overall size of the slopes. Let's think about E. In this differential equation, the y-coordinate is in the bottom of the fraction, okay? Which means that as you increase the y-coordinate, the slope should decrease in magnitude, right? As I make y larger, this fraction is going to become smaller in magnitude, like closer to 0, which means it's going to get flatter. So the slope field corresponding to this equation has to have the property that as y becomes larger in magnitude, the slopes are going to get flatter, okay? So which differential equation has that property? We've already sort of talked about 1 and 2. We've identified. does 3 have the property that as you make y larger in magnitude, the slopes get flatter? I don't think so. Like, starting here, for example, and increasing the y value, these slopes don't seem to be getting any flatter, which is telling me that this slope field doesn't belong to this differential equation. Well, how about this one? If I make the y-coordinate larger in magnitude, do the slopes get flatter? So starting right here and then moving upward, making that y-coordinate larger in magnitude, are the slopes getting flatter? I think they are, as a matter of fact, in both directions. So this is a pretty good candidate. I don't think that 5 has that property. As I go up this way, the slopes are not getting flatter. And I don't think that this one has the property either. So I'm pretty sure that E has to go with 4. So it's those kinds of arguments that you can make to match up differential equations with their slope fields. You want to be looking out for differential equations that only depend upon one of the variables. That will create a slope field which exhibits a certain kind of symmetry. And you want to be thinking about the magnitude, right? You want to be thinking about the magnitude of the slopes and how that will bear. Here's another trick. Another great thing to think about is what could make the slope 0? If we look at D, this quantity, x times y, is going to be 0 anytime either x is 0 or y is 0, right? If x is 0, then the slope will be 0, and if y is 0, then the slope will be 0. So whatever slope field belongs to this differential equation has to have the property that all of the line segments on the x-axis and the y-axis have to be flat. That's number 3. And I think that's the only one which has that property. Because if you look, along the x-axis, the y-coordinate is 0. Well, if y is 0, that's going to force this quantity to be 0. Slopes are flat. Along the y-axis, the x-coordinates are 0. So that's going to force this quantity to be 0 as well. So it's really those kinds of arguments that you want to be looking for in matching up the differential equations with their slopes. And that's what I was getting at here. You want to be asking, like, what would cause your differential equation to be 0? What would cause your differential equation to be undefined? Like, looking at this last differential equation right here, because there's an x in the denominator, this thing will be undefined anytime x is 0. That means that this thing should be undefined along the y-axis. So which slope field has that property? Well, that one certainly does, right? Anytime the x-coordinate is 0, in other words, anytime you're along the y-axis, the slopes are not drawn in this picture, which means the slope is undefined. I suppose maybe you could draw a vertical line if you wanted, but the program has chosen not to draw it here. Okay, let's do number 3. Below is the slope field dy dx equals x squared. So here it is. Sketch a solution through 0, 2, and then try to guess its equation. So I'm going to go back to my graphics program. I want to sketch the solution going through 0, 2. We talked about this a moment ago, how to do this, what this looks like. It's pretty simple. You just look for the point 0, 2. Which is maybe right here. There's 0, 2. And we want to sketch a curve flowing along the slope field as though it's like an ocean current going through this point. So if I start here, this first line right here is horizontal, so I should move a little bit to the right. And then I just kind of follow the direction of the slope field. So it's perhaps going like this. And then you can trace it backwards as well. So something like that. If you wanted to guess this graph, it does look like a cubic. It looks like a cubic that's been shifted up by 2 units. Maybe it's like x to the third plus 2. Possible, but there's no way of knowing for sure just from the graph. Now let's just solve this differential equation using separation of variables. Okay, so we need to get all the x's and y's on different sides. All I need to do is multiply both sides by dx. That gives me this. So the variables are separated. Now I integrate. So I integrate both sides. The integral of dy, that's like 1 dy. the antiderivative of 1 is just y. So I have y equals antiderivative of x squared is 1/3 x to the third, and then I got to remember my arbitrary constant. So it is some kind of a cubic like we thought. It's not x to the third, it's 1/3 x to the third. Of course, that's the general solution, right? If we want to know the particular solution satisfying this initial condition, then we need to plug in 0, 2 into this equation to find the value of c. So replace y with 2 and replace x with 0. I obtain this, which of course that first term vanishes, and I just find that c is equal to 2. Replacing c with the value I just found gives me 1/3 x to the third plus 2, and that's the particular solution. So that function right here, if you graph it in Desmos or your calculator or whatever, it'll look like this, the curve that we saw just a moment ago. Okay, so that's pretty good. I just want to draw your attention to this example that appears here. What I'm doing in this next section is I'm sort of preparing you to solve harder differential equations. The harder differential equations involve, well, absolute value and exponential functions and logarithms and all kinds of stuff. And I just want you to review a bit of those. So let's do a little bit of algebra review. Recall that the absolute value equation is really just two regular equations, right? If you see this equation, absolute value of x minus 2 equals 3, that really means that x minus 2 is equal to positive or negative 3. So this absolute value equation yields two regular equations. X minus 2 equals positive 3, x minus 2 equals negative 3. And then you just solve each one of those equations separately and you get your two solutions. This happens a lot. In differential equations, as we'll see, you have to solve these absolute value equations. So let's take a look at this example. Let's solve the differential equation dy dx equals xy with initial condition 1, negative 1. So what I do first is I separate the variables. I guess I multiply both sides by dx and I divide both sides by y. That gets me here. And then I integrate both sides. I need to find an antiderivative. Remember, the antiderivative of 1 over y is natural log absolute value of y. Okay. And then on the right-hand side, antiderivative is 1/2 x squared plus c. Don't forget your integration constant c. Now, I like to plug in my initial condition right away. That is right away after integrating. So I'll plug in this point right here, replacing x with 1 and y with negative 1. That gets me here. Now, we have natural log of absolute value of negative 1. Well, absolute value of negative 1 is just 1. So that's natural log of 1 equals 1/2 1 squared. So we get this. Natural log of 1 is equal to 1/2 plus c. Natural log of 1, that's the power of e, which gives you 1. That would be 0. So natural log of 1 is 0. So solving, we find that c is negative 1/2. Now that I know the value of c, I go back to this stage right here, the line I had before I plugged in my initial condition, and I replace c with the value we found, negative 1/2. So this gives me natural log of y, of absolute value of y, is equal to 1/2 x squared minus 1/2. Now, remember that the goal now is to get the y by itself, and the y is stuck inside of a natural logarithm. Well, the way to get the y outside of a logarithm is to exponentiate. So we're going to exponentiate by the base of the natural logarithm, and that's e. In other words, both sides of the equation become powers of e, right? So the whole left-hand side, natural log absolute y, becomes an exponent of e. The whole right-hand side becomes a power of e as well. And then the left-hand side, e to the natural log of blah is just blah, right? And that lands us here. Some of you may not have seen this word before, exponentiation. If you think about solving logarithmic equations in a different way, that's fine as long as you get here. But exponentiation by the base of logarithm is the way that I teach it. So we obtain this expression here. Notice the whole right-hand side is in the exponent, like this negative 1/2 is part of the exponent of e as well. And at this stage, we have to recall what I said a moment ago with absolute value equations. If you have an absolute value equation like absolute value x minus 2 equals 3, you drop the absolute value bars and you slap a plus or minus on the other side of the equation. And that's what we're going to do here. So drop the absolute value bars, put a plus or minus here. Now the thing is, we're not done, because there's supposed to be one and only one function which satisfies the differential equation and matches this initial condition. But because of the plus or minus, we actually have two functions written down. I promise that only one of them is correct, not both. To find out which one is correct, you should actually plug the initial condition in again. If you replace x with 1 and y with -1, we get here. Simplifying the exponent, the whole thing actually turns out to be 0, 1/2 minus 1/2. And then e to the 0 is just 1. So we find -1 is equal to plus or minus 1. Now, should you take the plus or the minus in order to make this equation true? Well, you definitely have to take the minus, right? It has to be, so therefore, the correct function is obtained by taking the minus here. So the correct final answer is this thing right here, okay? Okay, so that's plenty for today. Good luck and happy solving differential equations.